Hi, today we are going to talk about horizon dip, which is the difference between the mathematical horizon and the observed horizon due to geometrical effects. Now, the mathematical horizon is a tangent plane to the sphere and it extends to infinity in space. If you have a spherical earth, this is your mathematical horizon, and we measure a lot of things with respect to the horizon. We measure altitudes of stars, we measure sunrises, sunsets, and it is absolutely critical to know where the horizon is for surveying if you are using a sextant in the middle of the sea to measure your position and so on. But if you are at a height h above the surface, your tangent plane is not a plane, it is in fact a cone. This person, obviously not drawn to scale, can see a bit further away, and this distance is called the horizon distance dl. The angle between the mathematical horizon and the observed horizon is called theta, the horizon dip. Now, let us calculate what the horizon dip is with respect to the height. We are going to ignore refraction and we are going to assume that the earth is spherical. In the next slide, we will talk a little bit about how to include the effects of refraction, but the full analysis is extremely complicated. Our geometry is set up like this. We have an observer at a height h above the surface of the earth with a radius r. The observer can see along this observed horizon and they can see land to the distance dl, which is your horizon distance, and theta is the angle between the mathematical horizon and the observed horizon, which is the horizon dip. Now, you'll note that this theta is the same as the angle subtended by the arc dl at the center of the earth, and you can write theta is equal to dl by r in units of radians, of course. Now, you can also think about this right angle triangle which has the hypotenuse r plus h, and this side has a length r, and this angle is theta. So, you can write cos theta is equal to r divided by r plus h. So, now if theta is fairly small, you can use the small angle approximation to calculate theta, and for small theta we know that cos theta is approximately equal to 1 minus theta square by 2. So, equating 1 minus theta square by 2 to r by r plus h and simplifying, you can calculate that theta is equal to square root of 2h by r, and equivalently the horizon distance dl, because since it is r times theta, is equal to square root 2h into r. Now, of course, with atmospheric refraction this equation changes, but it is very hard to calculate, and the overall effect is that we can see further. If this is your observed theoretical horizon, with refraction rays of light can get bent through the atmosphere and you can actually see horizons which are much further. Now, this effect makes the planet appear flatter. The radius is larger than what you actually have. You can estimate it as r effective, where r effective is equal to r divided by 1 minus k. K is a factor between 1/6 to 1/7 depending on the atmospheric temperature, pressure and humidity. So, in summary, the observed horizon is lower than the mathematical horizon by this angle theta is equal to square root 2h by r. As you go higher in height, your observed horizon will become further and further lower than the mathematical horizon, and you will be able to see further.